Okay, so now we're going to do the Chem 1405 kinetics properties labs. Kinetics is talking about the speed of a reaction, how quickly or how slowly it goes. So you can have a spontaneous reaction. Yes, the reactants will react and give you products, but that has nothing to do with how fast the reaction will occur. Some are very, very slow reactions. Classic example is if you take a copper penny and you just lay it outside, it will turn kind of a green, blue as it oxidizes, but that's a very slow reaction. Right? Other reactions can be very, very fast. They happen in a couple of microseconds, literally. Right? And so there are various things that affect the kinetics of a reaction. The five we're going to look at today are, number one, the nature of the reactants. Right? Some acids will react quicker or slower than other ones will, perhaps. Right? Number two, I got to look at my list here. Number two, the concentration of the reactants. So do you have a really concentrated or do you have a very dilute solution? Generally speaking, the more concentrated, that means the molecules are crammed in, which means they're going to collide and hit each other faster, which means the reaction should go quicker. Right? So concentration, number two. Number three is surface area. Right? So how much of the reactant is exposed? Is it in one big clump like a rock, or is it like a powder that has been lots and lots of surface area because it's been broken up? That will affect the rate of reaction. Number four is temperature. Generally speaking, as we get hotter, molecules will move faster, so they collide faster, and so the reaction occurs quicker. Right? The rule of thumb is for every 10 degrees or so Celsius, the reaction goes twice as fast. Right? That's not a hard rule, but it's a common average rule you can think of. And finally, number five on our list, catalysts. Catalysts are things that just their presence alone in that reaction vesicle makes the reaction go faster. So classic example here is in your own body, enzymes. Enzymes are catalysts. They're proteins, but they make the reactions go faster. Say you ate lunch and now that lunch is trying to be metabolized. Enzymes are going to be present there to make those reactions speed up. Okay, so for our first part, part A, we're going to go over here. This is going to investigate the nature of the reactant. So I'll let Dr. Shin, who's running our camera for us, zoom in on this. And let me get the procedure so I can follow along. We have, in this part A, 5 different acids. Over here we have sulfuric acid, hydrochloric acid, nitric acid, phosphoric acid, and acetic acid. And we do have different concentrations on these. So for example, this is 6 molar. Right? And so 6 protons would come off, 6 molar, if that was totally dissociated. This one has 2 protons that could come off, so we have that at 3 molar. 3 times 2 is also 6. Nitric acid, there's only 1 proton that comes off, so it's 6 molar as well. So we're keeping it, the reactivity as far as the number of protons that can come off the same in each case. Phosphoric acid actually has 3, and so we're doing a 2 molar solution there. And acetic acid, again, has 1, and so we have a 6 molar. So they are on the same field as far as their concentrations and the number of protons that can come off. Right, so we've leveled that off. I hope that makes sense. We also have magnesium, and magnesium comes in these little strips. Is that good? Can you? Yeah. Okay. So little strip of magnesium metal. Magnesium metal is very soft. It's very flexible. I can bend it and such. But magnesium metal will react with acids, and so here we're going to investigate just which acids might react faster, just based on their nature, which acids might react slower. So, all right, so let's add 1 milliliter of each acid to each test tube. So let's just go right down the line. Sulfuric acid. This is approximately 1 milliliter down there. Number 2, hydrochloric acid. Number 3, nitric acid. Number 4 is phosphoric acid. 5 acetic acid. Acetic acid is the stuff that's in pickle juice and vinegar. So it's got that real distinct smell to it. Hydrochloric acid, number 2, there is the stuff that's in your stomach. And so, well, these are very familiar acids, actually. Phosphoric acid you find in Coca-Cola. So, anyway, we got our 5 different acids, and now the 5 different strips of magnesium. All right, next step, it says, prepare your strips. I've got them ready. It says, at the same time, or as quickly as possible, put 1 piece in each test tube. So I won't be perfect at this. Maybe get 2 at a time. I will very quickly try to get them all in at about the same time. So ready, set, go. Drop those in. Drop these guys in. And drop them. Let's see, we've got some reactions definitely happening. Oops, my paper fell. Some of them reacted very quickly. Some of them are still reacting, aren't they? So we'll watch that for a while. And you'll want to note which one was the fastest, which one was the slowest. Of course, the beauty of video is you can back it up and watch it again. You see the bubbling coming up from the various ones. That's, again, the metal reacting with the acid to produce hydrogen gas. And so those little bubbles are hydrogen gas coming up out of the solution. You can tell which ones are reacting quickly or slowly by watching for that hydrogen gas, and also, of course, watching for the disappearance of the metal. If the metal is totally gone, clearly it's reacted. So far it looks like no metal left, no metal left, no metal left here, but these 2 are still reacting a little bit. They still got the metal present. This one's almost gone though. This one's still bubbling. So we'll keep watching for a little longer. Actually, I think we're pretty much done. Let's see. This one has no metal left. This one has just a little microspeck left. All right. Actually, I don't see anything now. That little bit of, actually, there's just a little bit left, and this one's still going. This one, the other 4 are all dissolved, so no more metal left on those. Part B. Here we're going to look at concentration. Again, how crowded together are these molecules? How much do we have per volume? The reaction we're doing is the classic iodine clock reaction, as it's called. It's actually a 2-step reaction. It's in your notebooks. You can read about that. And when the first reaction is done, the second reaction kicks in and makes the solutions turn color. And so it's kind of fun. You sit there and you watch it, and you just wait and wait, and all of a sudden, boom, it changes color. Now, what determines how long it takes to change color? The concentration. And we have beaker A over here, 3 of them, and beaker B, 3 of them. In beaker B, we have the reactant, which is hydrogen sulfite, sodium hydrogen sulfite, the indicator, and water. Now, I've already gone ahead and I've mixed these together. They're identical, 3 identical beakers, just to save us some time on the video, so they're ready to go. In beaker A, looking at the chart in your lab manual, that should have both water and different amounts of the potassium iodate. And so I've already put the water in, again, just to save some time, but we need to add the potassium iodate. That's the one that we're going to change the concentration of then. A, B, and C, and I'm sorry, the 3 beakers of A. And if you look on the table in your manual, the first beaker will only get 2 milliliters of the iodate, the second one gets 4, and the third one gets 6. So quite clearly, the concentration is going to be increasing from 1 to 2 to 3. All right, so we'll start with the first beaker of each. We need to put 2 milliliters of the iodate into A. There we go. Got 2 milliliters. All right, so our 2 beakers are ready to go. Now we combine them together and we put the timer on to see how long does it take for the color to appear. Pour the B into the A, give it a swirl and start the timer. Start the timer there. Okay.
Supposed to be seen.
I don't know. There we go. Now we're getting some color. So hopefully you are looking at the timer, and you can back it up if you need to, but it changed color. It took about 3.5 minutes or so. You can get the exact time again for watching closely. All right. It's just kind of neat. I mean, it's just sitting there. It looks like nothing's happened, and all of a sudden, bam, you get the color change. All right, let's do the same thing. This time, trial 2. And this time, we're going to put 4 milliliters in. So twice as much. twice as much of the iodate. Mix that up. Start my timer, reset that. Okay, once again, we'll do the same thing. Add the B to the A. Start the timer. A little mix. And there it goes, just changed. Twice the concentration, definitely took much less time for that reaction to finish. And trial 3, this time we're putting 6 milliliters into A. So 3 times the amount of the initial. Go, there's 6. Pour that into A. Okay, this is a reset. We'll add B. Start, swirl that together. There we go. Color change. So let me just line these up. You see the color change, and this one is still solid, but you get the same color, more or less, finally for all 3 of them. But the kinetics, the timing of it was different because the concentrations were different. Part C. Here we're looking at surface area, and so how much of the reactant is available for reaction? Is it on the top, is it on the surface, or is it buried inside the particle? For example, here we have marble chips just look like rocks, right? These are actually calcium carbonate. And calcium carbonate will react with hydrochloric acid to produce, again, gas, this time CO2 gas, carbon dioxide bubbling up. One of the chips here, and it looks like that, just I got about a 0.5 gram chip in this weigh boat. And in this one I got about 0.5, but we're going to crush them up with my mortar and pestle first. And so this is just a bowl and my crusher, my mortar and pestle set, put that in there and grind it up. You might have seen this kind of a picture like on movies or pictures of old labs back in medieval times or whatever. It's kind of a, I don't know, it seems to be a symbolic sort of a piece of apparatus, very ancient, very old piece. But there we go, and I'll tip it like that. You can see we've ground them up into a fine powder. Okay. And so there's a lot of surface area on that. Actually, you know what I'm doing? Go ahead and dump this out back into my weigh boat. Okay, so here's our comparison then. We've got a solid chunk, or we've got it was ground up, so there's a little bit of surface area, or a lot of surface area. Those two. Okay. Let's go ahead and dump each one of these into a test tube. There's the ground up powdered one. And here's the one where we've just left it as a chunk. Okay, so surface area, here's our 6 molar hydrochloric acid. We'll go ahead and add about 2 milliliters. Maybe I'll do 2 squirts. Each squirt's about a milliliter to each test tube. And you can observe by looking at the bubbling of the CO2 being released which one is going faster and which one's going slower, so you can observe the kinetics. So here we go. There's one squirt here and one squirt here. That's a wonderful demonstration of surface area and a much faster reaction than the one that we ground up with the mortar and pestle than the one over here. And in fact, this one's slowing down quite a bit after that initial vigorous reaction, it's slowing down, and I think it's slower at this point, where this one's actually faster now because it's, well, it's still going, where this one's wrapping up, it's almost done. So this one had an initial very fast kinetics, and this one was slower. We can watch it for a little bit. Yep. This one's almost all the way out, just a little bit of gas now. This one's still going along. So again, the difference in kinetics, which one went fast, which one went slow. Part D, we're looking at temperature now. And I gave you the rule at the very beginning, on average every 10 degrees Celsius of a hotter temperature makes the reaction go about twice as fast. And so we're going to test that and see if it works. We've got, once again, the 6 molar hydrochloric acid in zinc strips. So we've seen that reaction already before. It produces the hydrogen gas and it bubbles. But we're going to do it in different water baths. We have one beaker here where it's just room temperature water, and we'll put our test tube down in that and kind of keeps it at room temperature. We've got this one where it's going to be an ice bath. We've got this one up here where it's going to be at about 40 to 50, maybe 60, a hotter one. We'll say about 50 degrees. First, let's go ahead and put, I'm going to move this up front, let's put 5 milliliters of the hydrochloric acid, 6 molar, in each test tube. So, let's get down here and pour this in. Okay, there's 5 milliliters in one test tube. Milliliters in the second. bit too much there. Although this is just the media that's reacting, and so a little extra or a little too little isn't really going to affect it. We're now looking at concentration here. Okay, so approximately 5 milliliters of hydrochloric acid in each test tube. One of them we'll go ahead and put in the room temperature water bath, like that. The second one, we'll go ahead and put that here in the ice water bath, so it's going to start to cool off. And the third one, we'll put it up here in the hot water bath. And then we'll get the reaction going. Now this is already probably at room temperature, so I don't need to worry about letting it come to temperature. The other two, while we observe this one will be cooling off inside the test tube. This one will be warming up inside the test tube. All right, so let's look at what is the temperature of the one at room temperature. There you go, you can see it. Yes, all right. So there's our temperature. We'll take our zinc strip, we'll drop it in that test tube and start the timer. And you want to see how long the reaction takes. So when it stops bubbling, that's when we'll call it. So I'll drop it in now, start the reaction. And hopefully, can you see that okay? Mm-hmm. All right, good. So we'll watch that reaction until it stops. to stir it up here a little bit. It's almost there. A little bit of bubbles still coming out. Just barely.
Seeing almost, right?
Almost gone. I can still see a little bit of that metal. Still just barely there. So I'll let it go just a little longer. All right, I think we can call it. It's just barely a little bit of metal there left, but I think we can call that right there. All right, so you saw the time. That was at room temperature. Push that one aside. Now we'll set my stopwatch. Now let's go ahead and do the one that's been heating on our hot plate and move that one into position. Excuse me. Let's go ahead and see what the temperature of this is. Hey, that's pretty good. We're trying to get 50 and we got 49.7. Not bad. Not bad at all. 49.9. So we're right there, just about 50, just about where we were supposed to be. Okay. We'll take our zinc, drop it in, and then we'll start the timer. Okay. And you can see just how rigorously, or vigorously, I mean, the bubbles are coming up. This is definitely a faster reaction when we do it at the hotter temperature. Well, it's almost stopping, isn't it? Give it a little stir there. And it's still going just a little bit. Give it a little bit longer. Not quite, almost. Okay. There's just a little bit of metal there, so I think we can call it at that time right there. So quite a bit faster when we did it at the hot temperature. Lastly, we've got the test tube that's been in the ice water. And check the temperature of that. As expected, we're right there, almost right at 0.6 degrees Celsius. Our last piece of zinc. Go ahead and take that and, whoops, I forgot to get the timer right. Reset it. All right, I'll drop it in. Hit the go button. It's just barely bubbling, as you can see here. So let's go ahead and put it back in and we'll let that react. see how this is going. We do have bubbling happening, but it's quite a bit slower. We're at 1 minute and 10 seconds here. What we're going to do is we're going to cut the video and let this go, and we'll come back when it's a little further progressed. Okay, we are now over 12 minutes, and there is just a little bit of that metal left, and at that cold temperature, that small amount, you barely see any bubbling at all. So that's just about perfect. I think we'll call it there at about 12.5 minutes. Much, much slower than the room temperature or the hot one. Part E. Here we're looking at a catalyst. Again, a catalyst is not part of the reaction, but its mere presence in the reacting vessel, whether it's a test tube or a beaker or whatever, its mere presence alone causes the reaction to go faster. The catalyst is not used up. You put it in, at the end of the reaction, it's still there. It's just its presence alone makes the reaction go faster. And I told you that enzymes in the body are catalysts. They're biological catalysts. So here we've got hydrogen peroxide. You can buy that in any pharmacy store. And hydrogen peroxide does decompose, produces oxygen gas on its own. So if you've got hydrogen peroxide that's sitting around for several years, it's probably not what you think it is anymore. It's mostly water at that point because the oxygen will have escaped, and that's what hydrogen peroxide breaks out into, is oxygen gas and water. So you probably have just a jug of water at that point. All right, so this will decompose, but it's a slow reaction. Manganese dioxide, which is this black powder, is a catalyst for the reaction of hydrogen peroxide breaking down. So we're going to see the effect of it. We've got two test tubes. One, we'll just put some hydrogen peroxide in and watch it decompose, or trying to decompose anyway. And the second one, we'll put some manganese dioxide in. All right, so let me do that first, actually, just to get that ready to go. It doesn't take a whole lot. I'm just going to do a little scoopful and put that into the second test tube, like there. Just hopefully you can see that. How's that? A little bit of manganese dioxide in the bottom of that test tube. And now our hydrogen peroxide. I'm going to put a squirt in. The first test tube, again, we'll just put it in by itself. Two squirts, it's about 2 milliliters. And this is kind of our control. There it is. We can kind of shake it up to see if anything happens there. But there's our normal hydrogen peroxide. It is decomposing. It is giving off oxygen gas, but it's a very slow reaction. In fact, we might be lucky to see a bubble or two happen there. And the second one, of course, we've got our catalyst already present in the test tube. We'll go ahead and put our 2 squirts of hydrogen peroxide in that one. 1, 2, and give it a quick swirl here. All right, and you can zoom in very closely on those 2 test tubes and see the difference having that catalyst mix. Watch that for a little bit. One thing that hopefully you'll notice is that the black powder is still there. Yeah, it's kind of mixed up because it's being bubbled up and so it's swirled up, but it's still black, it's still powder, it's still present. So the catalyst is not being used up, it is not part of the reaction. But quite clearly, we get all this hydrogen gas being produced very quickly compared to this one where, yeah, I haven't even seen a bubble yet. And so it's really speeding up the reaction very much without being used up itself.